Lesson 9-2, adding and subtracting rational expressions. So we're still on rational expressions. You guys remember rational ratio here, right? So we're talking about fractions. We had fractions of polynomials. Right, now, if you want to add or subtract two expressions, they have to have a common denominator is a key term here. Okay, and your book breaks out the acronym LCD as in least common denominator. Okay? So like maybe the simplest common denominator that you can have. Let's jump into some examples and see how these play out. Okay, so 1a, we got, all right, so a bunch of variables flying around. We got 7a over 4b, right, and then plus 4c squared over 10. Okay. Now, how do you add these two fractions together? Well, we're going to spell out this phrase. Common denominator. Okay. They have to have the same common denominator. Um, Maybe I should really back up and do a real basic example with you guys. Okay, like here, what if you have a couple of pizzas, okay? And maybe this pizza was sliced into like five equal slices, and this pizza was sliced into how about 10? Let's do 10. Right. Let's say they're all like equal slices, right? And let's say you eat most of this pizza, and you got like one slice left here, and you have three slices left here. One, two, three. Okay. Okay. And you would say, okay, let's just put this all in one box and throw it in the fridge, right? What do we have left? Okay. You say, hey, how much of a total pizza do we have? Okay, we have got one slice that's a fifth of a pizza here. We've got three slices that are each a tenth of a pizza. So how many total pizzas do we have? Well, it's really, I got one fifth of a pizza here. I got three tenths of a pizza here. Okay. Say, well, we could compare it and shove it all in one fraction. If only we could sort of like compare slices. And I picked an example here where maybe it's kind of obvious to see. It's like, well, what if you had sliced this pizza originally into 10? It's like, I know we did five slices, but what if I slice each of those in half? Well, really, it's like I have two tenth slices. That's really what this is. So if I take this one, or if I multiply by 2 over 2, right, 2 over 2, see, if I multiply by 2 over 2, the fact that this is equal to 1, that means I'm not really changing anything. What I am doing is manipulating the denominator. So that works out to be 2 tenths plus 3 tenths, right? Now I can directly compare these slices. Okay, so it's really like I'm going to have 5 tenths of a pizza. So by the time I get this mega slice on the left side and these three skinny slices and put those all together, really that works out to half of a pizza that I have left in my fridge. Okay. Right. So there's a kind of tangible example with pizzas, right, where I got a common denominator to go through it. Right. And the first example we're into, but well, it's a lot more abstract. It's got A's, B's, and C's and numbers flying all over the place. We can still use the same principle. Say, what does this 4B have that the 10 lacks and vice versa? Okay. Well, I definitely know on the right side I need a B, so I can multiply it by B over B. Again, the fact that this is equal to 1 means that's a valid thing. I can always multiply something by 1 without changing the value, right? But now I've got conveniently got a B in the denominator. That's nice. Okay? But what about this 4 and this 10? Well, yeah, let's see. If I break them into prime factors, I know 4 is 2 times 2. I know 10 is 2 times 5. So uh, how about 20? I think 20 would be the least common denominator. I'm gonna throw in the word least, but I'm thinking right. So least common denominator, I think could be 20. Like 4 goes into 20 and 10 goes into 20. Okay, think about prime factors so you get that too. Okay, so I'm gonna multiply this one by 5 over 5. Okay. Another way to think of it is this left fraction denominator lacks a 5 that this other one already has in it. Okay. Okay. Because that'll bring this up to 20b. Okay. And then this one over here, I'm gonna multiply by 2 over 2. Right? And then that will also become 20b in the denominator. Notice that everything in pink, this fraction, this fraction, this fraction, are each themselves equal to 1. Right? So it's a perfectly valid step to multiply anything by 1. Right, what have we got left here? So we got 7a5. So altogether that's 35a. Right? And then over here, I've got all these multiplied together. 4 times 2 is 8. And I got a b in the mix and a c squared. And now they each have the same denominator, which is 20b. maybe 2b, right? Which means I can push them together and make one giant fraction. So it'd be 35a plus 8bc squared collectively divided by 20b. Okay. That's probably the answer right there. Right? One thing I would check is could I simplify this anymore? Like C factors of 20 could be C 5 and 4. Well, 5 goes in 35, but not the 8, right? And 4 goes in 8, but not in 35. Yeah, or in both these terms in the top don't have, I mean, one has a B, but not the other. So yeah, that is as simple as that can get. Right, and that would be the answer. A, B, and C could be any set of numbers, and the original expression and my giant single fraction represent exactly the same value. Ooh, that's pretty fun. Let's do example two. Example two. Ooh, got a subtraction going on. Got a 2x plus 1 all over x squared plus 2x minus 15. Okay, so that fraction. Then minus, and then 7 over 5x minus 15. Okay. E. So we got a couple of polynomials for denominators. What I'm really thinking to do here is to factor each of these and see, hey, maybe something in common will already pop out. Here, let's see what happens. So 2x plus 1 over, now how could I factor this? How about 3 and 5, I think could work. Let's do x plus 5, x minus 3. Let me show you guys that works by FOILing. X squared, bing. Negative 3x plus 5x is 2x, bing. 5 times negative 3 is negative 15, bing. Okay. So do that. And then minus, and over here, well, here I know I can factor out just a plain 5. So let's do 5 and then x minus 3. Yeah. Okay. Yeah, we're on a good track here because now these denominators do have something in common, which is the x minus 3 bit. Right? So that's fine. That's already in place. Right? But they also each lack something the other has. Like this 5 over here. This one on the left sure could use a 5. So I'm going to multiply it by 5 over 5. Again, by multiplying by 1, well, this part's equal to 1, right? That's a valid step. And this part on the right really needs this x plus 5 piece. So if I have x plus 5 over x plus 5, okay. Again, that peak part itself is equal to 1. So that's a 1 right there. Okay, so that's a valid step. Okay, so next step, this 2x plus 1 gets multiplied by this 5 up here. That gives you 10x plus 5. Okay. And then I'll say minus, and then this is 7x. And then 7 5 is 35. Now, since it's being subtracted, that negative is still going to distribute and get 35 up here. Notice I'm putting this now on one giant fraction because at this point it will have the exact same denominator, which is x plus 5, x minus 3, and then, well, a 5. I'll just put the 5 in front. It'd be like that. So, right, let's combine my terms up here. So 10x minus 7x leaves me with 3x. Then 5 minus 35, that's like negative 30. All right, it's all over 5, x plus 5, x minus 3. But there's something else I could do. I could pull a 3 out of the numerator. Actually, I'm just going to squeeze it into this corner right here. If I pull a 3 out, I can do x minus 10, but then it's not going to simplify beyond that. Same denominator, 5, x plus 5, x minus 3. Okay. So that would be a nice answer right there. Okay, so that right there. All right. Example 3. Got a word puzzle. The rate at which some oil wells pump oil and thousands of barrels given X years of pumping. Okay, so time is passing on with X number of years. Okay? And then the rate you can pump oil is going to get a change as a result. Okay, it's given by this expression. Simplify this expression. So example 3. Copy down exactly what they got down here, which is 20 over X plus 200x over 3x squared plus 20. Okay. So some about thousands of barrels. What would it be? Thousands of barrels per day, maybe? Right, you're talking about rate. Yeah, anyway, regardless, just do the math here. Okay. Notice a lot of these, I'll leave some space here because maybe I'm leaving space to multiply by something over something so to get a common denominator. Yeah. Um, ah, this one's, wow. Okay. This one, I can't really factor in a way it's going to be helpful at all. The only thing I think I can do is multiply this entire top and bottom expression by 3x squared plus 20. So the other guy's denominator gets multiplied top and bottom. Oops, I should have put that in pink ink, but you guys get this is equal to 1. Okay? And then I'll do plus, and then same story on the other side. I got a 200x already up here, and 3x squared plus 20 already down here. Okay? We're going to multiply this top and bottom by x, simply x over x. Again, to point this out, this bit right here equal to 1. This bit right here equal to 1. That's why this is going to be a valid substitute. Now, these two fractions do have a common denominator. Okay, so the common denominator is this right here. 3x to the 3 plus 20x, or I guess you could have left it factored, okay, no difference. But the numerator, now what? Well, this 20 is going to distribute into each of those terms. So that gives 60x squared plus 400. And then over here, this is plus 200x squared, so go like that. Okay. Now, I do have a couple of x squared terms, so a lot of those together. You guys see this is going to create 260x squared? You see, could pull out a 10. Why not? So let's pull out a 10. 26x squared plus 40. All right, I guess there's different ways you could write this. Maybe I should have left that x factored out. I don't know. 3x squared plus 20, something like that. Okay, I don't think this is really going to so much simplify. Okay, did they? Okay, I'm looking over here at the book. Did they finish it? Yeah. So their last step looks pretty much what I did. They just didn't factor this 10 out, although you don't have to. Okay, so there's a couple ways you can write it at the end. So that's a valid way. I decided about that. Let's see. Ooh, fractions within fractions. This looks exciting. Example 4. We're looking at x over y, and then the whole thing plus 1, and then divided by y over x minus 1 over y. Ooh, fractions within fractions. Okay, crazy. Okay. There's probably a few ways to handle this. Starting from the numerator, I would multiply this by y over y so that I get a common denominator within that larger numerator. And then down here, I'm going to multiply this by this little piece by y over y, multiply this by x over x. Therefore, these two fractions will have the common denominator xy, and I can push those together. Okay, so one step at a time here. So I got a big old fraction. On top, I got xy. Sorry, that's not true. X. There's a common denominator y. And up here I had x plus y. That's what I had. Sorry, there you go. X plus y. Okay, so it's x plus y all divided by y. Right, then down here, I've got y squared over xy. And then this is x over xy. And I'm subtracting. So I'll go like that. Okay. So at some point it's going to clean up and look like that. Okay. Now, a fraction over a fraction. You guys remember a little thought cloud over here. If I have a over b divided by c over d, okay, so one fraction divided by another fraction. Remember, that's the same thing as a over b multiplied by d over c. You could take the bottom fraction, flip it reciprocal, and multiply it, which I think would be a good next step to do. Let's try that. So I got x plus y collectively divided by y. Then we say multiplied by and flip this bottom fraction. So make it x times y over y squared minus x. Okay. Now, the one thing I say I can do from here is this y is going to cancel. I think that's the only thing you can do to simplify. Okay, I mean, you could distribute this x into the x plus y if you want to. I don't know if it's necessary. Okay. If this was an Alex question, I would probably type what I'm writing right now. Square minus x, like that. Okay, so I think that's probably pretty good. See how the book wrote. or this one, x squared plus xy over y squared minus x. Yeah. Okay. So the only thing your book did is additionally they distributed this x and made this x squared plus xy. Okay. Otherwise, it's the same thing. Same thing. Looks pretty good. Pretty good. Example 5. Simplifying complex fractions. So looks like a pretty similar example, I think. We got x over y plus 2 over x. And this is collectively divided by x over 2 minus y over x. Okay. So the top side here, this little fraction needs an x in the bottom, so I'll multiply x over x. Because so I can start to match this one. Okay. And this guy over here needs a y over y. Okay. And now, bing, they have the same fraction, or same denominator, have a matching denominator. All right, let's move on down here. This guy needs an x over x, so that this x matches this x. And this guy on the right side needs a 2 over 2. All right, and now, bing, now these guys do have matching denominators. Great. So they're making some good progress. So rewrite this here. I got x squared plus 2y. This is all divided by xy. And this whole thing is divided by, I got x squared minus 2y collectively divided by 2x. Like that. Okay. Again, fraction over a fraction. So I can take this bottom fraction and flip and multiply it. That's it. So x squared plus 2y over xy multiplied by 2x over x squared minus 2y. Now I do see this x. It's going to go away. Okay. And I think that's all you can do. I think that's it. So maybe I'll shuffle this 2 in front. Your x squared plus 2y. You could distribute that too. That'd be okay too. And then down here, I got x squared minus 2y. Yeah, I don't think that's basically going to simplify anymore though. Right. So I would probably just type that into Alex if that was an Alex question. Let's see, is that what your book came up with? 2x squared plus 4y over x. Whoops. Oh, I missed this y right here. That's okay. I can multiply that right here. There you go. Right. All right. So now we're back on track. X squared y minus 2y squared. Yeah. Right. So this that I boxed in is a completely valid answer. So that's good. And your book did do one extra step as they distributed this 2 on top and also this y on the bottom. So you could write it that way too. All right. So I highlighted some ahead of time. Got these highlights. Number 11. I got n over n minus 3. And, well, I'll leave a little space there. Do plus, and a big old fraction, 2n and plus 2 over n squared minus 2n minus 3. There we go. Yeah, so first thing I'm thinking is I want to take that denominator I just wrote and factor that. Let's do over n minus 3. Leave a little space. And then 2. I wonder if I should pull it 2 out. Nah, I'll just say this is 2n plus 2. Let's go with that. Okay. And then down here, okay. Now I have a suspicion already that one of the factors is going to be n minus 3 so that it matches this. I might be wrong, but let's see. I need an n and an n. Okay, 2 numbers multiply. Well, it's got to be -3 and plus 1. So -3 plus 1 is n squared. Bing. N minus 3 and is -2. Bing. -3, bing. Yeah. So, okay. Now compare these denominators because they do have the n minus 3 in common, but this guy on the left side is lacking something. He's lacking the n plus 1. So I'll put it there as n plus 1, but I'll also balance out the equation by writing it on top. Okay. Again, this part that I just wrote in pink is equal to 1. That's why this is going to be a valid step. I can do this. All right, so next step, I'm going to distribute this n up here. And that's going to go n squared plus n. Right. We'll be able to tie these two fractions together because they definitely have the same denominator of n minus 3, n plus 1. So that's common. Okay, and then over here, I got plus 2n plus 2. So plus 2n plus 2. Okay. I think the only other thing you can do is just group these together to make 3n. Wait a minute. I say that. Here, let's see what happens. I just considered, I wonder if you could possibly factor it after that. Uh, yeah. Yeah, you know what? I think there is a secret step after this. Ooh, this might become a little bit more exciting. We're about to find out. Okay. So let me factor that numerator and see where else this adventure goes. So I think it's n plus 1, n plus 2. So n squared, bing, 2n, n is 3n, bing, 1, 2 is 2, bing. Yep, it's all there. Yeah, here I got n minus 3, n plus 1. Aha, look at here. That cancels. Okay. So this does simplify more interestingly. N plus 2 over n minus 3. Yeah. Also, don't forget the good condition n is not allowed to equal -1. Because even though we canceled it out, right? Had you had it there originally and you plugged in -1, this would go to 0. So you would be divided by 0, which is why you're not allowed to have it as -1. So we'll throw that specific value out of the solution set. But otherwise, it's the simplified ratio right there. Yeah, that expression. Just like that. Pretty good. At 13, electric potential. The electric potential between two electrons is given by a formula, takes the form 1 over r plus 1 over 1 minus r. Can you simplify that? Like push it all into one giant fraction. Well, this left side needs 1 minus r down here, so I'll also write that on top, 1 minus r. And this right fraction needs just the plain r, so I'll multiply by r over r. So do you guys see what I just did? This is equal to 1. This is equal to 1. Right, so good so far. Okay, so it's 1 minus r, and then it's all divided by r, 1 minus r. Okay. And then over here, plus this r, so plus r. Okay. Which, oh, look at that. Cancel. So I think the answer is this. Like that. That should be it. Okay. We do a little numerical. Yeah, let's say, for example, if r is equal to pi, just to throw a crazy number at it and see what happens. Okay. We go back to the original statement. What is 1 over pi in this case plus 1 over 1 minus pi? What is that? So 1 over pi plus 1 over 1 minus pi. Okay. Looking at negative 0.1486 something something. It's going to go on. Okay. Now, what if I plug pi into my simplified expression? I've got to get the exact same number, otherwise I messed up somewhere. So what is 1 over then pi 1 minus pi? Okay. It looks different, but is it really the same thing? It should be 1 over, and then in parentheses, make sure you put parentheses here. Okay, that's fourth step. I got pi 1 minus pi. Come on, say oh yeah, it is. Negative 0.1486, something, something. Yeah, it's a match. Bing, bing. This is this. It's the same thing. Okay. So the way the book originally wrote it, straight out of the book, and this version I boxed in, it's the same expression. Sure is. So it's next here. Number 17. 17. I got 4 over x plus 5. Right, and then leave a space. So plus 9 over x minus 6. Okay. This whole thing divided by 5 over x minus 6. And then label a space minus 8 over x plus 5. Okay. Yeah, I think that's right. All right, so nothing crazy new, but it's probably going to be a lot of little steps. That's all right. So this fraction needs an x minus 6 over x minus 6. I'll eventually distribute this 4 up top. Right? This fraction on the top right needs an x plus 5 over x plus 5. Right? And do you guys see how the setup's going? Right. These two fractions will now have a common denominator. Right? I'm eventually going to distribute this 9 into the x and the 5. How about down here? This one needs x plus 5 over x plus 5. Yeah, same thing, distribute, distribute. Okay. And this fraction on the bottom right needs an x minus 6 over x minus 6. Okay, distribute the 8 eventually. All right, so a lot of little steps. It's all right. So 4 times x minus 24 plus 9x plus 45, all divided by x plus 5, x plus 6, or minus 6, I meant. There you go. Okay. And then that fraction is divided by a completely different fraction, which is going to be, well, we'll have the same denominator. That's interesting. So I'm sure that'll greatly simplify here pretty soon. Okay. But here we got 5x plus 25 minus 8x. And then two negatives make a positive. That's plus 48. Woo! Okay. Fractions within fractions. Okay. So I'm going to take this bottom fraction, flip and multiply it. Let's do that. While I'm at it, maybe I'll clean up a little bit too, right? Because 4x and 9x gives me 13x. And then negative 24 plus 45 is 21. So 13x plus 21. This is divided by x plus 5, x minus 6. Okay. Okay, I'm going to multiply this by, and here I got x minus 6, x plus 5. Okay, so just this right here. And then, here's the same thing, clean this up a little bit. This is it's like negative 3x, and then what's 25 and 48 is like 73. So plus 73. Is 73 prime? I think it is. I can't think of anything that multiplies to that. Okay. All right, so you good? Okay, and then last step is let's shove this all together. Got 13x plus 21, all divided by negative 3x plus 73. Looks pretty good right there. Yeah. All right, 26. I got 5b over 6a, leave a little space, plus 3b over 10a squared, leave a little space, plus 2 over ab squared. Yeah. All right. All right. Oh, so now we have three fractions. Okay. And remember, the rule is they just have a common denominator. Okay. So see, this first one has now 6 is 3 times 2. You know what? Right. Well, in terms of the numbers, I think 6 and 10 both go into 30, right? So if I was just focused on the numbers, 6 times 5 is 30, 10 times 3 is 30, and then 1 times 30, right? So I do need to multiply this by 5 over 5, and multiply this by 3 over 3, multiply this by 30 over 30. That'll bring all my numbers up to 30. 6 and 5 is 30, 10 and 3 is 30, and 1 times 30 is 30, okay? If you thought about that from prime factors, 6 is 3 times 2, 10 is 5 times 2. So this guy on the left needs a 5, this guy on the right needs a 3. Okay, that's maybe I should have explained it that way. Okay? But there's some other stuff. So this middle term has an a squared. Well, this first term only has a single a, so it needs another a. So multiply by a over a. And this one over here on the far right side also needs an additional a, so multiply by a over a. Okay. But then what about this b squared right here? only the last term has a b squared. And these first two terms need that. So I'll do b squared, and b squared, b squared. Yeah, I think that'll do it. Should do it right there. Okay, so put this all together. Um, Here's one giant fraction, and then plus, and then here's a giant fraction, and then plus, and then here's a giant fraction. Okay, everything in pink reduces to one. Everything we've been doing. So 5 is 25. I got an AB cubed. By the way, all these fractions have the same denominator at this point, so I may as well just put it all over the same thing, which is 30 a squared b squared. Right. At this point, every single one of those, you can get a good look at it and confirm for yourself. Yeah. Every single one of these has the denominator 30 a squared b squared. Yeah. Right, how about this middle piece here? 3 by 3 is 9, and b to the power of 3. Yeah, I think that'll take care of that. All right, and this last one got 60 and an a. All right, so be like that. Um, can I simplify this at all? Well, 25 is 5 times 5. 9 is 3 times 3. Okay, and those factors have nothing to do with each other, right? Fives and threes. Yeah. Oh, okay, yeah. So I can't really simplify it beyond that. I think this should be the full answer right here. Whoop. There it is. Sorry. Yeah, this should be it. It's pretty good. All right, and one more. Oh, do here. 36 lenses. Oh, yeah, but it has to be the lens one. Right, see if you're standing in front of a lens, right? There's a similar, I think you used the same equation actually with mirrors, right? Some of you guys may have seen this demo from my physics class. Ooh, actually, this kind of works on camera. Okay. Right, see, there's like a little ghost pig here, but the real one's down here. But if you're standing in front of this actually, it's a really good illusion. Works really well. Looks like you want to pick this guy up, but he's not really there. Right. And what this has to do with, if I pull this apart, are these parabolic mirrors, right? There are these parabolic mirrors going on. Right? They're like this. A little big and UFO looking deal, right? Right, so this will warp the image and maybe create something like this. And what they're saying on number 36 is that the associated equation, this is also straight out of a physics book, is 1 over p plus 1 over q equals 1 over f, right? And the physics story that attaches to these variables is f represents the focal length of the lens or the mirror, right? So basically how curved is the mirror you can quantify in f, right? And the p and the q stand for the relative positions of the object and the image, right? So in this case, right, here's maybe an object and an image. Yeah, something like that. So what do you hit? Focal length f of a lens, yep. Right, so is related to the distance of the subject front to lens, which is called P. Yep. Oh, they even gave you a picture here. Here it is. There's F, there's P, and then the distance from the lens to the image, Q. Okay. Express 1 over P plus 1 over Q as a single fraction. Oh, yeah. All right. Yeah, we do that. So multiply this by Q over Q, multiply this by P over P. And that will give you Q plus P over PQ. That could be 1 over F. Okay. I think that'll work. That's a wrap on 9 too.